Hi everyone and welcome. Today we're taking a closer look at the design strategies and materials that are shaping the future of battery technology in e-mobility. I'm Joe Staller, Senior Research and Development Chemist at Resins. For 20 years, I've been developing epoxy and polyurethane systems for the automotive and electrical industries. I'm excited to share what we've learned, especially around thermoset elastomers. I'm joined by Luke Workman, Chief Scientist at Electric Goddess. His deep expertise in high-power, efficient battery design extends to powertrains and system dynamics, where he comprehensively understands how to make EV powertrain systems endure the most extreme environments. Luke and I are going to have an open discussion where we'll educate each other and hopefully bring you some new insights as well. We're diving into the evolving role of polymers in battery technology, why it matters, where it's headed, and how engineers can design smarter, safer battery systems for e-mobility. After a quick tour of my family's winery, Staller Estate, we're going to jump into the conversation and explore how smart design and material choices are driving the future of EV battery packs. We're thrilled to have you with us. Let's get started. What are the key e-mobility battery pack design pressures and considerations? So when engineers are looking at this design that they need to make, what are the big things that they're most worried about or looking at?
Well, the constant pressure you have as a battery engineer is your gravimetrics and volumetrics with respect to watt hours per kilogram and watt hours per liter. These are what people judge you by as a battery engineer on your packaging efficiency. What actually matters though, and I didn't know this as a young battery engineer, but what actually matters is number one is making the safest, most robust product that won't be recalled or become a fire risk. And that really needs to be number one. And then your gravimetrics and volumetrics should fall as a secondary concern to that primary objective being achieved first.
Are you seeing that kind of shift toward that? Are people starting to realize that as these engineers are starting to realize this change in a hierarchy a little bit?
You see it on second generations of battery products a lot,
sure.
Where they decide to take safety and corrosion resistance, vibration resistance more seriously because now they've seen what happens if you don't address those issues sufficiently the first time.
What material properties matter most to battery engineers? They're coming to you, or they're looking at how they're going to do this potting. Mm-hmm. What properties are they first coming to you being concerned about?
Obviously, it's got to do the job of protecting against corrosion, and that's a huge part of its function in the battery. But I love with your resins its attributes in thermal runaway protection, where it can allow cells to enter thermal runaway, whether they had a manufacturing defect or you're initiating a safety test, and to quench and cessate that propagation effect. And your materials have the ability to do this better than any other materials that I've personally tested in thermal runaway propagation testing. One
thing that's really interesting that you just mentioned is cell quality defects, right? Mm-hmm. No, not all cells in a battery are created equally, right? I mean, there's always going to be flaws.
No two are created equally.
No two are created equally, right?
Everyone's a snowflake if you look carefully enough.
Yeah, so you can never be assured that all the batteries are going to perform equally. So from a manufacturing and an engineering standpoint, you need to say, okay, what do we do knowing these are snowflakes, these are all a little bit different. Mm-hmm. How can we, keep them all safe, right? That's the idea. How can we, and so it's the next level of the process, right? The battery's made, the next level of the process is going to be potting it and protecting those batteries, right? Mm-hmm. And talking a little bit about, the safety of having a fully encapsulated battery that has fillers in it that can mitigate thermal runaway. And how we accomplish that, it's really neat. So we have a number of different types of fillers that we can use in a system. One of them is really unique in the fact that when it gets to a certain temperature, it actually has an endothermic reaction, right? And that endothermic reaction pulls a ton of heat out of whatever it's around when it's at that temperature.
And carries it away.
And it carries it away. And at the same time, it's that endothermic reaction is happening, it's giving off water. So you're getting this self-extinguishing effect. And then this water, which has a huge heat capacity, right, is carrying heat away. So you have this, I like to think of it, it sounds silly, but almost this like localized fire department, right?
It's true.
Almost around that battery.
It's like having fire suppression, you could call it heat suppression really rather than fire suppression, I suppose. But it's right in the location you need it between the gap in cells so that it can carry that heat away from a dangerous initiation of the next cell. And you were asking about what the difference it makes in a battery pack. It's the difference between one cell initiates, whether you had a manufacturing defect, a cell defect, whatever caused the initiation, But one cell initiates in that safety test and all the cells have burned in the battery pack in, say, as little as 10 seconds. Or with your product in that same assembly, you can have that same initiation cell in the same location and have it cessate and self-extinguish, and the event is over with no additional cells entering runaway, which is a phenomenally improved outcome. The difference between, say, losing your house if it was in your garage or your living room at that time, or having a stinky smell in your living room or garage, it's a very big difference in outcomes.
Absolutely, and that's just talking specifically about one of the tools we have in our formulating process. There's also other flame retardants that can be formulated into a system that, in the event that you actually do have flames occurring, that it actually self-extinguishes those. So you not only have, this endothermic reaction, this phase change polymer that's helping to reduce mitigation, but if there is a flame, then now you have all this flame retardant.
Like bromine radicals, or
there's a number of different flame retardants that we can use. We can use halogen. We also have halogen-free materials if customers are concerned about halogens in their product. And all of these would be classified under what UL 94V0. Which that is a vertical flame test where you actually have to take a very small square. Yeah, you know what I'm talking about.
So you put surgical gauze underneath it.
Yep,
and if the gauze lights from
exactly. You put a flame underneath this and you take it away, and it has to go out 2 different times and less than 10 seconds. So there's a number of different test procedures, but the amount of flame retardant and thermal runaway mitigation material we can put in a non-cellular material is a factor of 100 more than you can put in a cellular material. So again, ratcheting up that level of safety that's available for an engineer's potting and encapsulation.
Well, there's a draw towards foams because of the density reasons. As I mentioned earlier, engineers in batteries get judged off their gravimetrics at the end of the day, and people care about how many watt-hours per kilogram you packaged. And so having a material that promises a lower density per cc is often the first place engineers jump. The thing you were trying to do by using the foam, you were compromising the material strength and integrity and thermal performance and all these different attributes because the goal was to save weight. But really, I think the more mature approach is to design for the non-cellular potting approach that has only the potting where it needs to be. So you mitigate the excessive volume because the cells only need to be encapsulated in as little as, say, 1.5 to 2 millimeters perimeter is enough to offer the quench material of your filler to be able to make the difference between surviving a salt fog test as well as surviving passive propagation mitigation. And when you design around a low potting volume like that, your gravimetrics are minimally impacted. It may even be your best gravimetric solution out of all the options, depending on how well of a job you can design for that potting.
Epic Resins has a lot of history in doing is electronic component encapsulation and potting. We've been potting electronics for over 50 years. Some of the first potting that existed for actually CRTs, your old television.
Yeah.
There was a thing called a flyback transformer that was on there that ran at very high voltages. So you needed to have a material that would insulate those electronics very, very well. And that's one of the places where really electronic potting started. So we have long history of potting. Taking that same technology that's been used in underhood applications, high voltage applications, fits perfectly into battery management systems.
Oh, yeah.
What are you seeing folks doing for their battery management systems?
Years ago, there was a press for battery management systems to have high bleed currents. And so there was an emphasis on thermal dissipation even in the BMS.
Sure.
But as the industry has evolved a bit and has learned it's better to LUT a pack die that has a cell with a high self-discharge current, because otherwise it will continue to off-gas. There was nothing the BMS could do to correct a defect inside of a cell. There's only things it can do to electrically, balance cell voltages, but this doesn't actually repair a defect that's causing excessive gas production. So today, the dominant thing they look for in pottings in a BMS is encapsulation, protection from, corrosion, obviously, vibration, corrosive vapor intrusion. These are the dominant things we're looking for in a BMS protectant, whereas in years past, thermal conductivity was a big attribute folks were looking for as well.
Got it. So you're seeing that's kind of the standard. The standard of the industry is really to pot the battery management system, right?
It's critical because there's too much voltage to, if it was a 12-volt circuit board, let's say, then maybe it would be optional if we potted it or not, because if it failed, you'd swap it out and, that'd be that. But when you have, say, 100 volts to 500 volts on this system, now a corrosion problem isn't merely, this electronic stopped working. It's a fire, often a molten salt bridge induced fire, which it only takes, one drop of salt water on an unprotected circuit board with the right voltage gradient to catch that board on a fire that may lead to burning the whole vehicle to the ground. And so the stakes are so much higher that it's not merely it stopped working. It's we might have to buy a new house for this customer sort of risk. And so they
so more critical than the battery, really, right? Because if the BMS if the BMS has a corrosion issue, it can set off the battery. Do the safety standards that exist, are they rigorous enough for BMSs and or batteries?
No, in my opinion, they're woefully inadequate, and often standards are formed by folks that have never seen the real world reason why they're testing that to know how to validate it effectively. One weakness of the test, just to call out something specifically, so I'm not just bashing them without giving reason. All the tests that involve a constant temperature at salt fog, like a typical standard is, say you're held at 50 C or 60 C, and you're in this saturated salt spray, environment. This has no ingress cycle. You're at one constant temperature, so the lungs have never taken a breath during the whole test. So it doesn't really matter if the test runs for 96 hours or 1 month or whatever. You have never taken a breath of what it'll feel like in the real world.
Yeah, it's not the real world at all, because every day you're getting multiple cycles throughout the day.
That's right. So I like to run tests where it has to involve a cooling cycle. In fact, lots of people run the test hot because they want to accelerate the thermokinetic process and the Arrhenius process of the corrosion happening faster. But I'm actually heating the product simply so it can cool and have that ingress cycle, which then makes your salt fog testing worth it and valuable. It's a false positive to run these standards by the book and you leave saying we don't have a problem, but in fact the first time you're in the real world you'll be cooling under the presence of corrosive vapors, and in which case you will take them into the assembly, condense them internally. If you're not potted. If you're potted in a product like your material, you can survive those tests where you're cooling in a corrosive environment all day, all night for years and suffer no consequences.
And how rigorous are the tests for specifically flame retardancy, right? Let's say in this situation where they are running a thermal cycle test, they are doing the test correctly, but then you have a flame event. Are those tests rigorous enough?
Well, a lot of test labs, just to give you an idea, a lot of test labs won't allow batteries in their salt fog chambers anymore because they've been burned literally too many times, and they don't want the smoke cleanup cost at their lab. And so it's a common experience.
And we have a number of different ways that we can modify the flame retardant properties. We can have things, materials that are flame retardant down to millimeter thicknesses. And larger than that. So, whether we're using, we talked about it a little bit already, but we talked about brominated materials, we talked about halogenated materials, we also have non-halogenated materials. And bringing these different parts and pieces into this formulation for those types of tests.
Is it a mechanical strength trade-off? Like as an engineer in the resins, if you could just have a magic wand and make them all this highest level of flame retardant, you would, why not make them safer, right? But there has to be some trade-off that you make on the polymer side.
So there's a balance between loading and also wet out of those. So what works best is you have to get good wet out of that particle, because then it becomes part of the composite, right? Mm-hmm. In reality, when you're adding a solid particle into a polymer system, you're really making a composite. Mm-hmm. So in many cases, you can improve properties like strength properties. Depending on the ratios of filler and the particle sizes, you can sometimes improve some of the elastic properties and the thermal cycling properties. And thermal cycling properties is really interesting, because you have to remember most solid particles have a much lower coefficient of thermal expansion than the polymer itself. So that's another formulating aspect that we can integrate into a system to improve the thermal conductivity, right? Mm-hmm. That's going to improve some of the
thermal expansion.
Reduce thermal expansion, in reducing thermal expansion, it reduces that breathing effect, right? Mm-hmm. Because you have a solid material, you're also expanding, contracting, but at a significantly lower weight,
orders of magnitude
of air, but also within the realm of polymers, right? Mm-hmm. Every polymer, depending on how it's designed, is going to have different levels of coefficients of thermal expansion.
Even its glass phase will make a difference in CT.
At EPIC, we have a TMA. And a TMA is where you put a glass probe on top of that polymer sample and you cycle it from the lowest temperature you want to the highest temperature you want. And getting back to that molecular structure to property relationship, we can adjust that molecular structure to give us a coefficient of thermal expansion that's appropriate for the customer's operating temperature range, in addition to making sure that TG is outside of their operating temperature. Perfect. And that's so important, because as you've seen, operating a material through its TG can cause huge stresses and huge problems, and even chafing. Can you talk a little bit about how that can affect chafing?
Every time it goes through glass transition, you go to a new density, a new volume. It has migration stress, creep effects. All of these things are exemplified during the glass transition. It's almost like the activation energy for any stress that it had been maintaining elastically to normalize in a creep deformation and yield, and even yield bonds and lead to crack formation. So every pass through the TG is a dice roll for causing damage in a stressed assembly with the polymer.
Of course. So in addition to that, that thermal cycling effect, in your experience, do you find that cellular materials or non-cellular elastic materials protect from chafing better?
Well, the foam materials have the most expansion and contraction stresses on the assembly, which causes the most relative motion, and more relative motion against surfaces means you're chafing through dielectric layers, and protection, sheathing, even wire harness abrasion is all increased in a foam's expansion contraction stresses over a solid potting, which the pottings that have good adhesion to all the surface interfaces in the assembly, your chafing risk approaches zero because your relative surface motion is approaching zero. You have adhesion to the interfaces.
How does that affect the lifespan of that battery system?
Well, there's a few places that chafing happens inside batteries. One is at the cell level itself, and the main cells that are affected by this are pouch cells. They have a foil envelope that they are laminated inside of, and this foil envelope only has around 20 microns of polyethylene for a dielectric barrier on the outside of this foil. So to chafe through this, it's something that if you had a sharp edge on your fingernail, you can just cut right through 20 microns of polyethylene. And if the cell has surfaces, particularly aluminum as it forms that sapphire oxide, where it's in contact with this material, it only takes extremely small motions in the range of thermal expansion contraction stress over time to defeat that dielectric barrier on that pouch insulation.
You really need to have something that's going to seal it, really, in the end, right?
That's right.
So that's where a potting compound is going to seal better than obviously a foam material, a cellular material, right? Because when you have that damage on that polyethylene film, that's where your ingress is going to occur.
Yep. There's, cell technologies reaching the threshold where they will outlive the customer in many cases. Jeff Don's lab, which is in Nova Scotia and does some cell research for Tesla, but they have cells that cycle hundreds of thousands of times, so many times that a car would need to reach tens of millions of miles of driving before the cells were worn out, which is unrealistic to expect. Yeah,
I'll take that car.
And it's a situation where the only way that an end user will have, when that technology is in your cordless drill, for example, the only way you'll need to buy a new cordless drill battery is if it wasn't protected from corrosion, vibration, impact, chafing, whereas a situation like potting will make batteries be effectively immortal. A battery doesn't intrinsically have to wear out just to cycle. It wears out often from its defects, from nucleation points, from side reaction effects that are not part of its energy storage and release process by design intent. They're all the things that happen not by design intent that cause it to wear out. And so as you improve, as you reduce imperfections that cause aging, batteries can last, indeterminate amount of time. The greatest honor a battery engineer can have is for their cells to actually reach end of life by someone wearing them out. And this almost never happens without a fully potted design, for the reason that corrosion kills them. We have a battery recycling company, and most of the packs that we receive there, the cells, 99% of them will be at some nominal health and capacity still. And some area was not protected from corrosion adequately and has failed. And that's the reason why the whole pack gets frozen and
that's
shredded.
very costly. And it's costly also from a consumer perspective, right? This battery only lasted so long. Mm-hmm. Why do I want to buy batteries? Why do we want to invest in all this battery technology when they don't last as long? We have a number of times where we'll have an engineer that says, hey, but I need this to be designed for recycling. And it always amazes me. I always wonder to myself, well, are you designing a product to last, or are you designing it just so that
to go straight to the recycler, or you want a service period first?
Exactly.
But there's some big misconceptions.
Because you own a recycling company.
That's right.
Too.
We have a recycling company, and we hear this all the time too. That people tell us that, oh, we're sorry, but we can't recycle their battery pack, and we're like, and I'm always curious to hear the reasons why. And sometimes they'll be like, oh, our case is here, or the cells are glued in with this, or we potted it in some material, And it's like, well, the first step of our process is we freeze it, and then it goes into a shredder that shreds engine blocks.
You freeze it below the point of the TG.
Yeah,
the glass transition temperature, which for those folks that aren't familiar with that, that's the temperature at which the material goes to become a glass type material. Mm-hmm. So it's very easy to break apart.
The shredder doesn't actually care if you're potted or not. It cuts through steel. It cuts through the gears in a transmission. It cuts through drive lines. It cuts through engine blocks. And so when you put your potting in there, it's probably a soft place.
So you've kind of debunked this. Okay, we don't have to worry about if you're potting. It's recyclable either
That's
way.
Right. Either way, you end up as shreds that we recover the nickel, copper, lithium, and cobalt from.
So let's go to the whole other end of this process of manufacturing, right? And talking about the ease or the challenges that manufacturers have with potting, right? And versus a foam material. One of the things I find very interesting with the foam material, we talked about it a little bit, we'll readdress it here, is the variation in the amount of foam and the cell structure and all these different things that you have to put in place in your manufacturing to make sure you're getting consistency versus an elastomer. An elastomer is a two-component material. It's metered in. It's actually mixed just like a foam is mixed, but you don't have to worry about getting the right cell structure, all the right bubbles. You pot that into there.
Get it on ratio and get the right amount in, and you've achieved success.
You've achieved success. So
even if the pack is 10 degrees hotter that day or 10 degrees cooler that day, you've still achieved success.
You can still achieve success, exactly. Yep. Versus with the foam, you have now rework.
That's right.
It's interesting to see the difference in the volumes that you'll get, right? In some instances, on one day, you'll have a 5-degree difference from one day to another. But what people don't realize is that 5-degree temperature difference is a huge expansion of air.
That's right.
Air expands many, many times with very few temperature or very small temperature changes.
The thermal kinetics of where it'll kick gas bubbles is changed too. Nucleation sites and
nucleation is so important. Exactly. When you're frothing polyurethane foams, if you don't froth them right time after time, you're going to get a different foam structure. And when you get a different foam structure around every single battery that you make, it adds a lot of questions in. Non-cellular potting compounds, you don't have to worry about that at all. You're going to fill it up with a solid material, and you're not going to have any bubbles in there, and it's going to be completely encased. So it makes the manufacturing process much easier for the manufacturing engineer, and then obviously you're building a safer case there.
I love that your products degas well, so that in a perfect world, the moment the last gas bubble has risen out of it, then it gels and you move on,
And we can adjust, and that's another thing, we can adjust how easily a material flows. So that way, when a process engineer is looking at how am I going to get this material in these tight spaces, we can do a number of things from a formulation standpoint and a compounding standpoint, whether the material has filler particles in it or no filler particles in it. Making sure that material gets to the places it needs to get to. We understand the importance of that, and we understand how to adjust a formulation in order to make that happen. So we talked a little bit about potting with foams, and one thing I don't think a lot of engineers realize is those same foams that are used for potting batteries can also be used to lift concrete. And it's quite amazing the amount of force that polyurethane foam can produce when it's actually what they call blowing or foaming up. Have you ever seen that actually breaking cases before?
Oh yeah, it swells panels on cases. It'll lift sheet metal cases. In fact, that was something we learned with foams early on was if you overfill or it overexpands, it lets itself out. Anywhere, you might have a fill port that you would like it to let itself out, but it has the force to lift seams and allow it to exit anywhere you want it.
And that adds a lot of cost. I mean, it adds cost because number one, you have material coming out that you're wasting, right?
The cleanup too.
And the cleanup, and in many manufacturing processes, and a lot of these are automated, when you now have to have a person going in and going through and taking a knife or some type of and a hazard, right? Cutting through some of this foam to try to clean it up. Are you seeing manufacturers seeing the cost of that and pivoting not only for the other safety and all these other properties that elastomeric materials have, but also because of the cost of manufacturing?
Definitely. And we've done assemblies where it required slicing the foam off, kind of like you'd slice the top of a cake off too, which is extra labor, and now it leaves a bunch of open cell interfaces too. And the foam structure collapses so much from cell surface energy that you can often, when you cut the top of that foam off, the muffin top of the foam off, you can often look right down and see wetted, cell perimeters because of that foam collapse. It'll look great on the top of the foam, but as soon as you go next to the can walls where it matters the most, that structure is all collapsed and kind of like it looks like it melted or something, but it's really just bubbles popping.
You get these much larger domains, these much larger cavity domains. And the other thing that's important to know too is now you have this extra material that you have to responsibly dispose of.
That's right.
All right. So that's an added cost as well. The manufacturing downtime with foams can also be a challenge because if you're not frothing, you're not getting the right cell structure, you're constantly trying to readjust In your experience, when you're seeing a foam process versus an elastomer process, are you seeing a difference in the downtime that a manufacturer has on each of those?
Definitely, and the amount of rework too, because if that module comes in just a few degrees colder, then the foam rises a centimeter or two lower, and if it comes in a few degrees hotter, it rises overfill, and they have to cut it down. But we see far more rework and far more wasted modules from foam processing, unfortunately.
You're not only making your manufacturing process easier, in many cases faster, and then you have the lifespan of that product, that you're improving the overall lifespan
and the risk when it comes to batteries,
which is a greater cost almost.
That's right. The lower risk, people often think in a battery game that their big risk is if they have to warranty replace them all. But the big risk is actually if you ship a fire hazard and you have to buy real estate. Nobody's business case works out for buying homes every day, that you get the ash pile of the home rather than the value of it.
Luke, I want to revisit the gravimetrics, right? And this concern about gravimetrics, because we hear it so often. What about that engineer out there that wants to have his cake and eat it too?
Well, I once focused so hard on gravimetrics before safety and before everything else, but as a more experienced engineer, I was able to find that with potting you can meet that balance between exceptional packaging efficiency fractions, mass fractions of your packaging overhead, as well as extremely high gravimetrics in a monolithic encapsulation. If you design from the ground up around being encapsulated, a lot of people give potting a bad name because they took their large, full of air voids and cavities shell design.
Absolutely.
And they fill it up with 5 pounds of material and they say, oh, this is crap, it added 5 pounds. But
that could have been designed to hold only 2.5.
Or even 1 or half a pound, and that's where your gravimetrics can still be achieved. Don't give up hope. You don't have to say, I'm going to have poor gravimetrics because I'm potted.
Sure.
You can have that cake and eat it too, but it takes designing around using the least amount of the potting. So the potting needs to be in the places it needs to be for functionality. And for propagation resistance, this means that everywhere that's between cells needs to have it. For corrosion resistance, this means everywhere that has electricity on it needs to be encapsulated. Sure. And but it doesn't need to be more than that. You don't need to have half an inch of it around all of these surfaces, that's just dead wasted space. This is why you can really make efficient gravimetrics with very high mass packaging fractions. And
from a design perspective, starting that design early, right?
That's right.
As I've done some calculations, I've found that when you look at the difference between a foam, the weight of the batteries, right? I mean, if you're looking at the weight of a specific battery, then you encapsulate the outside of that with like 2 millimeters of foam versus 2 millimeters of urethane.
Makes a very small difference.
It makes such a small difference. Right. I mean, you might say, okay, the whole battery is a number of pounds heavier, but the battery itself is already a huge investment. There's a lot of time and energy that go into making that efficient. And then in the end, that you don't protect it.
On the topic of gravimetrics with your foam example too, with that 2 millimeters of foam versus 2 millimeters of your potting material, the 2 millimeters of foam will not be mechanically robust and will require an additional shell housing perimeter to offer mechanical integrity for that assembly, even just to lift it and move it around without damaging it. And so this is one difference where you may already win gravimetrics, not lose gravimetrics to the foam, but win gravimetrics to the foam, in that you're a caseless assembly because the polymer has an integrity that is as strong as other people's plastic. I think we're often more robust because the case has discontinuities in its strength, in its mechanical integrity, where there's a boundary between the part that's case and the part that's assembly internally. But with your product's adhesion to make a monolithic structure, you lose that impedance mismatch between the case and the housing inside. When you run vibe tests, for example, in things that are in housings, they're always having micro motions in that housing. You know, when you do your teardown afterwards, every part that was touching that case will be chafed and worn.
Sure.
It'll have witness marks where it wore the metal down that was touching. You know, it wore, you know, polished all these edges and interfaces. But when you pot that pack in a monolithic potting encapsulation, and you undergo that same vibe test profile, you know, you only see where it interfaced to the table. There'll be witness marks where it wore on the vibe table platform itself, but through the whole assembly, you don't see any of them because the relative motion between surfaces is controlled so much better when you're bonded in a monolithic assembly rather than when you have cohesive, resonating assemblies inside of a shell. You know.
In addition to gravimetrics with cars, you know, that's what everyone thinks about. They think EV, they think cars, but we have all these other places where batteries are being used. You know, electric bikes. You know, we're seeing the electric bike industry really embrace solid potting. And they're seeing great longevity from that. Heavy equipment, right? Heavy equipment, you know, they don't have to worry about weight, right? That's not a big deal for them, but they're seeing huge efficiencies. We also have the ability from a polymer formulation standpoint to tailor a material to the densities. Even if you're looking at a solid elastomeric material, we can tailor those densities to fit closer to what your really desires are.
Can you tell me about some things that are levers you can pull on the potting side to say that I make a design and I'm crying that it's a kilogram more than I wanted? Is there something you can do to reduce the density but still remain a solid that offers the protection of a solid? Yes,
absolutely. So, you know, we can optimize the filler level. So let's say we're just talking about that endothermic reaction that some of our fillers give. You know, we can try to optimize how much of that do we need in there and maybe reduce that level some. Let's say it's thermal conductivity that you want. Different types of fillers give different thermal conductivities, and those different fillers have different densities. And we talked a little bit about how we optimize particles and particle size using our laser diffraction particle size analysis at EPIC. We can also leverage that we have the right ratios of particle size to optimize particle contact to get the right thermal conductivity that you need. Let's say you come to me and you say, hey, we don't want fillers in there. We want to go with a solid non-cellular material, but we want it unfilled. Well, we have VZero materials that can fit that bill and kind of anything in between. So
that's great.
Yes.
What kind of thermal conductivity values is your low end? Like, let's say that I want a solid material, but thermal conductivity is a penalty for this location.
So generally you're about 0.2 watt per meter Kelvin. So in any material that has no particles in it at all, you're about 0.2. There might be, you might get a little variation from that. But then anywhere from there up to 3, we can adjust the thermal conductivity of a material. I almost feel like you could wrap up 3 main items that we're looking at here. I think the one over-encompassing everything is really, really safety, right?
Yeah. That's right. Yeah. If you have to recall it, it wasn't actually a bargain to your company. It's bad for the industry. It's bad for your company's name. It's very expensive. If you don't do what it takes to ship a safe product the first time, like monolithic potting encapsulation, it only costs you more money. You might have thought adding potting to the line cost, maybe it's $100,000 for the machines and equipment, and you might have thought this was too costly. But recalling the product, it usually starts at millions, and if there's real estate purchases involved too, you get to tens of millions very quickly, and that small investment for $100,000 for the potting machines and equipment would have looked like such a bargain for your company if they could have had that foresight.
I saw an interesting report of an ocean-going car carrier that actually caught on fire.
These battery fires, when they're not designed in potting that can resist propagation, those car carriers, I feel bad for the crew on board because they're trusting that there's not one QC defect in those cells, one jagged foil edge burr on edge foils in the electrodes, and that could catch fire, at which point they activate the ship's fire suppression, and the batteries don't need oxygen. They work off of CO2 displacing oxygen from those assemblies, but the battery cathode liberates its own oxygen to burn, and so you have a a new level of fire safety that normal methods don't protect against, and it can take that whole ship down.
Sure.
From a single foil defect that's just a few microns in size can take that whole ship down.
That investment in safety also kind of then leads to giving you better longevity and reliability of the battery. Because you're protecting that battery and it's a safer battery, it's going to have more longevity as well.
That's right. Yeah. You'll have less warranty replacement, under a best case, and your company will stay in business because it's not, its brand hasn't been destroyed by fire reputation and purchasing homes. So it's really like a non-starter to ship a dangerous product.
Sure. And then that third thing of manufacturability, right? Under the big things that we've talked about, it's going to be easier to process urethane, a non-cellular material. You're not going to have the extra expense of trimming and the amount of pressure, right, that foam can put on a case.
That's right.
So the ease of manufacturing is also going to be improved with a non-cellular material.
Yeah, and the consistency too. The reduction in fallout is huge when you go to pouring in as a liquid with a constant volume and curing as a solid with a constant volume is so reliable and dependable to have on your line. Absolutely. Compared to needing to have a phase transition and blowing bubbles.
Awesome. Yeah. Well, Luke, I appreciate it. This was a really great conversation. I learned a lot from you, and I'm really excited about the information that we've shared with our guests today.
It was such an honor to see your amazing lab at Epic, and thank you for teaching me so much about polymers, and most of all, thank you for the incredible safe products that I've been using in batteries for many years now with great results.